Haskelle, I'll give you a quick intro. Um, Haskelle Trigue White is joining us from Corvallis, Oregon. Woot woot. She is a senior geoscience major at Oregon State University and is now a geochemist technician for a hydrogeology lab researching how land topography influences terrestrial water and soil processes. The Tanaka Scholarship that she received from the Pacific Northwest chapter of the Association for Women Geoscientists helped her to apply for and complete a NASA internship working under a planetary geochemist at the University of Arkansas. And so we're super excited to have her here, super excited to see several people. I forgot to mention the Zoom housekeeping. March already mentioned if you're not the presenter, please mute yourself to avoid the background noise. If you want to save bandwidth, you can turn your video off while Haskell is presenting. If you have ideas, questions, well, Haskell, this is a question for you. Do you want questions during your talk or kind of held to the end? How would you like to run that?
I'll wait for the end. We'll hold on.
Okay, great. So if you're burning question, you pop it in the chat so you don't forget it, and then we'll go through those at the end, and we'll also have an open discussion. So thank you all for being here. I will turn it over to Hess.
Thank you so much, Melanie. I'm going to share my screen, get that set up. Okay. Awesome. All right. Thank you. Hello, everyone. It is really nice to see you all. I'm very grateful for the opportunity to speak to you all today. So as mentioned, I won AWG's Janet Cohen Tanaka Scholarship last year and have been invited to give a presentation. Today, I decided to split my talk into two sections. First, about my overall undergraduate experience, specifically how I navigated academic opportunities to get to the position I am in today. Then, I will present the research from my NASA supper internship last summer. I wanted this talk to be helpful for fellow undergraduates who might need help figuring out academia, but I also wanted to highlight the actions that my mentors have done for me to help me succeed. Many of you are in a position where you could be a mentor to undergraduates or younger, and I hope through my presentation you can better understand the perspective of a current student. I will highlight the actions and guidance that made me feel supported that could be of use in your own mentorship. And I also just wanted to highlight the accomplishments that the AWG scholarship has allowed me to pursue. So we'll start with how I found geology. I graduated high school in 2020 when the major shutdowns of the COVID-19 pandemic first started. My school district decided to graduate all its seniors in March 2020, so I had a lot of time to think about what I wanted to do. So after completing my high school's expeditionary program, I initially thought that I wanted a career in engineering, and I knew I wanted a career related to space, but I personally was not excited by the duties and responsibilities of an aerospace or mechanical engineer. So by chance, I came across an article by Dr. Eric Clemente titled "Dear College Students, You Should Take Geology," and I was sold. I was captivated by the interdisciplinary aspect and the ability to do field work, laboratory work, theoretical modeling, and more. I knew I could apply a background in geosciences to the space sciences field in a meaningful and interesting way as a planetary geologist. So, a week before my first week of classes, I switched to a major in geology, and soon enough, I was taking Geology 201, the introductory physical geology course, on my first day of college. I loved my introductory course, and I felt fortunate to find a major I was truly passionate about. But going into college, I had no idea what to do besides go to class and maybe stumble upon a summer internship. I didn't know about what extracurriculars to do, what scholarships to apply for, didn't really fully understand the concept of grad school. I didn't even know undergraduate research was a thing. A lot of this was made more difficult by the fact that all my classes were online and I was not living on campus. I was really lost and I didn't know how to reach my goal of becoming a planetary geologist. What I did know was that I was going to be around a lot of experienced people, so I decided to talk to my Geo 201 professor after class on that first day of school, and I asked him point blank how to best succeed as someone who learned what geology was a week prior. That first meeting was crucial, and I wanted to highlight it as my first tip. Connecting with faculty or professionals in your field is going to help you a lot. That meeting introduced me to the idea of undergraduate research, and my professor taught me about RAU's and OSU's URSA program, which is called Undergraduate Research Scholarship in the Arts. Reaching out to people also shows initiative, and it helped my professor to know who I am, remember my name, and it gave me a connection to someone who wanted to see me succeed. Throughout that term, I kept going to office hours, asking questions in class. I kept my camera on in Zoom during lectures. It definitely pushed me out of my comfort zone, but I gained valuable knowledge and a mentor. By the end of the fall term, my Geo 201 professor, Dr. Kaplan-Yeltsin, told me to make a list of professors whose research I was interested in. I told him I was interested in working with a hydrogeology group listed on OSU's URSA program, and he contacted the advisor, Dr. Pamela Sullivan, who accepted me into her lab. Not only did reaching out provide me with research experience, but it introduced me to a lot of academic opportunities I didn't know existed previously. So one piece of advice I always share is to use your title as a student to learn as much about your field as possible. It's kind of like a superpower. Professionals are more often than not very excited to talk about their work with students and love answering questions. So talking to faculty, hearing their perspective, maybe even shadowing their workday is a great way to gauge how much you would enjoy being in your chosen field. A lot of my mentors have showed me scholarships, including AWGs, that have allowed me to focus on these extracurriculars. The connections you make will help you throughout your career. Everyone I've mentioned thus far is still helping me, writing me letters of recommendations, introducing me to new opportunities, sharing valuable insight every time we talk, and some are even here today to support my talk. So at this point in my journey, I am participating in a research project. So during URSA Engage, I worked on a project that studied the evolution of soil pore space and its effects on terrestrial processes. My job was to assist graduate students in soil sieving and pH tests. I used this opportunity to gain as much information as I could about research, and I did this by asking questions. So don't be afraid to ask. I was brand new to research during this time, and I often had no idea what I was doing, and that's totally okay. You're not supposed to be an expert, and it will be someone's responsibility to teach you the basics and train you on lab techniques. That is exactly what Dr. Sullivan and her graduate students did for me. For example, I didn't know how to read a scientific paper at first. The first paper I was given was about multi-stripe laser triangulation, which we use to quantify soil pore metrics. And I remember the first time I read it, I don't think I really learned anything because it was really hard to understand and it took me forever to read the paper. So I asked one of the graduate students what tips they had, and they recommended that I read the abstract, the introduction, and then the conclusion to understand the big picture, then move on to methods and discussion to learn about all the smaller details. And there really isn't one good way to read a paper, but the fact that I was told that I didn't have to read the paper from top to bottom was just a complete game changer for me. A lot of times people take these soft skills for granted, so it's up to us undergrads to ask those questions. Being in a research lab gave me the opportunity to move to Corvallis and do in-person work. During online school, this was an invaluable experience. I was super excited to be doing something offline. During this time, I helped grad students conduct field work and laboratory work which aimed to quantify soil structure that could be related to the soil's response to land cover changes over time. We wanted to produce objective data regarding the movement of gases between the soil and the atmosphere that we can compare with structural information from, for example, MLT scanners to determine if the changes in land use create systemic changes in soil structure. This required me to learn R, MLT scanning and analysis, root size image analysis, pH and electrical conductivity measurements. I learned a lot of new techniques in a short amount of time, and this proved to be very useful. Anytime one of the graduate students needed training for a new technique, I would join the training if they had the bandwidth to take me in. Even the trainings I rarely use today are valuable skills that expanded my lab knowledge and are skills I can put on my CV. It also makes you a valuable and reliable asset to the group. Dr. Sullivan has even asked me to train other graduate students and newcomers to the lab. So by the end of my first year, that marked the end of that URSA Engage program. Part of that requirement was to prepare a lightning talk video for OSU's Celebrating Undergraduate Excellent Conference, and I did. I received a lot of positive feedback and really good questions from that video, especially from Dr. Sullivan. She was really impressed with both the video and my performance throughout the program, and she offered me a paid research fellowship for the summer and the next school year. That summer, I continued to work on the soil pore evolution project, and I did well enough that Dr. Sullivan pushed me to write an abstract for GSA's 2021 conference, which was accepted and approved for oral presentation. I presented in GSA Connect's 2021's recent advances in paleoclimatology and paleooceanography session, and my abstract was published in their conference journal, so that was my first DOI, and that was really exciting for me. My advice here is to sharpen your presentation skills and to watch other presentations from people in your field. Watching talks at GSA and at OSU introduced me to new topics and taught me how to give a presentation. These presentation skills can showcase your ability as a researcher, and it's one of the reasons why I got offered a paid research position, because giving a great presentation reflects both well on you and on your advisor. After GSA, Dr. Sullivan asked me to lead and design an independent research project in the same area that her other graduate students were studying. It's called H.A. Andrews Experimental Research Forest. This was during my second year of college, but all the skills I had gained through presentations, laboratory work, field work, writing skills, computer skills, it all gave me the confidence and ability to be trusted with this task, and I was really proud to be given that opportunity. I decided to study the weathering patterns in the soils from nearby Cascade volcanic arcs. This research also contributes environmental data from the Pacific Northwest that could determine how land topography influences terrestrial water processes important to the vitality of the region. To do this, I learned even more lab and field skills. So first, literature review was used to select sample collection locations and analytical techniques. To collect samples requires field work, so I have dug soil pits, learned how to install gas sensors, acquired soil cores, and learned how to keep a field notebook. Lab work was spread between several labs, including OSU Soil Health Lab, the Keck Lab, and 2 of Dr. Sullivan's labs here in Wilkinson. Not only did I acquire new laboratory techniques, but I also learned how to effectively collaborate with other scientists. The main techniques I used were microwave digestions to convert sediment into solutions. Then I used ICP OES, inductively coupled plasma, optical emission spectrometry to determine the elemental composition of the soil. I'm actually almost done collecting data, so I'm currently finishing up this project by plotting the results as tau plots in R. I hope to present these results in the near future, and so the advice I have here for successfully conducting independent research is collaboration. Research in geology especially is inherently interdisciplinary, and I worked with a lot of different people. While I use this to gain a lot of experience, I also use these collaborations to learn how to be a good researcher. It's also important to remember that the people around you have a lot of valuable insight, but so do you. You are a part of the collaboration, and people can learn from you. When I started to recognize that, I felt a lot more comfortable in research. So, during the time I was in the thick of microwave digestions, about midway through my second year, one of my field camp instructors introduced me to AWG's Janet Cullen Tanaka Scholarship, which I felt very confident to apply for thanks to these experiences and a wealth of supporting people. I ended up winning, so I decided that I was ready to start thinking about graduate school. Dr. Sullivan and I designed a project that would give me a variety of research experience that I could indirectly apply to planetary geology, so I decided to apply to a planetary science internship. I found NASA's Summer Undergraduate Program for Planetary Research, SUPR, through Caltech's internship website. So my tip here is to let universities find opportunities for you. OSU has Handshake, and our college, or my geology college, CEOS, frequently sends emails listing tons of internships, jobs, and fellowships. Since OSU doesn't have a planetary science program, I found schools that did, and I searched on their websites for a while. Thanks to all my research experiences and networking and scholarships, especially AWG, and thanks to OSU's geology program and all my mentors, I got accepted into NASA SUPR, and now I will present the research that I did last summer, which was at the end of my second year of college. So NASA SUPR provided the opportunity to conduct graduate level research in planetary geochemistry using complex models and space science facilities. I was paired to work with Dr. Vincent Chevrier at the University of Arkansas, where I was assigned to study the geochemical conditions on the surface of Venus during the possible transition between past habitable conditions with stable liquid water and the present-day hot and dry environment. Some background on Venus is that it is the hottest planet in our solar system with an average surface temperature over 470 degrees Celsius and an atmosphere over 90 times as thick as the present-day Earth. Venus and Earth very likely had similar formations given their similar size, mass, bulk density, and a very similar initial volatile inventory. However, Earth has been continually habitable since the Enhadian, whereas Venus became uninhabitable. So at one point, their evolutionary pathways diverged, resulting in profound and unexplained differences in both atmospheric composition and dynamics and geophysical processes on the surface and interior. These differences remain unexplained because geologically, Venus is a very difficult planet to study. Hundreds of millions of years ago, Venus experienced a global resurfacing event that occurred due to infrequent volcanic activity that caused a near instantaneous change to the Venusian surface. This event may have caused Venus to become the hothouse it is today, but it also buried all earlier material, obscuring its geologic history. Despite this, we have evidence that Venus may have been habitable. In the late 1990s, Pioneer Venus recorded an in situ measurement of deuterium to hydrogen ratios that was about 150 plus or minus 30 times greater than terrestrial water. So that implies that Venus had a shallow ocean for much of its history, with one estimate up to 525 meters of liquid water if spread evenly across the surface. General circulation models and coupled interior atmospheric redox evolutionary models have demonstrated a habitable climate with stable liquid water as early as 715 million years ago, which is quite short on geologic timescales. Something occurred on Venus that caused the Great Climate Transition, transforming it into its present-day state. We don't fully know what that something is yet, but there is speculation it's related to frequent volcanic activity and perhaps large igneous provinces during the global resurfacing event, contributing to a runaway greenhouse effect. So why study Venus? Because even though it's difficult to study Venus's obscure geologic history, understanding when and why the evolutionary pathways of Venus and Earth diverged is crucial to understanding how terrestrial planets form and how their atmospheres and surfaces evolve. NASA has recognized this importance and have approved 2 missions to Venus this decade to measure the atmospheric composition and geologic history to figure out what happened. And thus, because of that, it's being hailed the Decade of Venus. The European Space Agency also has a mission that I don't know as much about, but so that's 3 missions to Venus this decade. It's really cool. Until then, until we get those missions going, we need to use existing data to identify the most useful measurements we can make on the surface and atmosphere to figure out whether Venus was habitable, and if it was, what happened. To understand the Great Climate Transition, we present a thermodynamic model of Venus's geochemical evolution during this transition period to find mineral and gas markers indicative of earlier atmospheric conditions. We did this by using GeoChemist Workbench, specifically the REACT module. This program models equilibrium states and geochemical processes and systems that contain an aqueous fluid. It can calculate the equilibrium distribution of that aqueous species, calculate the fugacity of gases dissolved in that fluid, and trace the evolution of that system as it undergoes reversible or irreversible reactions in an open or a closed system. It can do a lot, and many of you are probably familiar with it. I really enjoyed working with it. To provide a conceptual model of the work we did, REACT begins a simulation by calculating the system's initial equilibrium state. The program then changes the system by adding or removing reactants to vary the system's composition, change the temperature, or vary the fugacity of gases in an external buffer. So in this figure, for example, we have a system containing aqueous fluids and minerals that remain in equilibrium as its composition, its temperature, or both change over the course of the reaction path. So changes in composition can reflect the explicit transfer of reactants into or out of the system, or the implicit transfer of buffering or gas fugacities and species activities. To model Venus's transition from habitable to inhabitable, we simulated the equilibrium paragenesis between various crust models of primitive ocean and the atmosphere. We then changed the temperature, so we have those initial equilibrium conditions, and we changed the temperature from 20 degrees Celsius to 300 degrees Celsius, and then we view the results of the evolution path. To go into a little more detail about the initial conditions, this is to simulate the primitive ocean. I use standard concentrations of seawater on Earth with an average temperature of 25 degrees Celsius. This model provides an approximation of a stable liquid water ocean during a clement period or temperate period. The typical concentration of chlorine was dedicated as a charge balance and maintained the neutrality of the fluid while minerals precipitated. I then added 7.5 micrograms per kilogram of aluminum to the solution because there's plagioclase present in some of the crust. So this is the average concentration of aluminum in seawater due to the dissolution of clay minerals, and this will satisfy that plagioclase feldspar present in nearly all basaltic rocks. I also added 3 milligrams per kilogram of iron, which is typical of ocean water because igneous rocks also tend to have iron. The crust is where I had some fun here getting this parameters. So for the final project, I decided on 3 crustal compositions. When I was initially doing this, I think I worked with 6 to 8, but for the final, I think these three were the best. So the first composition is tholeiitic basalt, which comes from observations from Venera 13, which is one of the few in situ measurements we've ever attained from the Venusian surface. Venera 13 and all the Venera space probes are from the Russian Space Agency. So that's how we got these compositions, and most of the Venus surface is basalt. It's heavily basalt. The other 2 compositions have not been directly measured, but come from the exciting research into Venusian tessera. Tessera is the oldest stratigraphic unit on Venus, and according to the average surface crater retention age, it's about 300 to 800 million years old. Therefore, tessera may be the only rock unit from before the global resurfacing event. This provides rare insight to the first 80% of the planet's history. So while the rest of that basalt is from the global resurfacing event, this might be from before it. We have not measured the mineralogy or the chemistry of these terrains, but the tessera folds we observe could come from silica-rich rocks if the crust is dry at the time of folding. We were really curious to see how these rocks would react in the Great Climate Transition, so I used surface emissivity compositions attained from VITRIS, which is the Visible and Infrared Thermal Imaging Spectrometer that's aboard the Venus Express. And using Gilmore et al.'s 2015 paper, they interpreted these measurements to be of granodiorite and anorthosite compositions, and thus the major oxides of granodiorite and anorthosite were used for the other 2 simulated crusts. We use 3 different partial pressures of carbon dioxide. We have a 100 bar model for the present day atmosphere, which is about 96 bars of pressure. Then we have 50 bars and 1 bars to model potential earlier atmospheres. So 1 bar would model potential temperate atmosphere, and 50 that transition to the current day. The pressure is fixed in each of these simulations for an open system. For redox conditions, both oxidizing and reducing conditions were tested using the electron activity in aqueous solutions. A PE of 13.05 was used for oxidizing conditions based on the iron 2 plus and iron 3 plus redox couple, and then we used a PE of 2.407 based on the SH2S redox couple that was used for reducing conditions. All of these initial conditions were implemented, and the model changed the temperature from 20 to 300 degrees Celsius to represent that heat-death transition. The program then calculated the most stable phases of minerals and gases and recalculated the pH and PE at each iterative step. And then we got some results. So I got a lot of graphs showing the mineral, fugacity, aqueous species, pH, PE, all showing the evolution of the surface on Venus. Today, I will only show you the mineral results. I will show the results for all 3 crusts at all 3 pressures, but only in oxidizing conditions. Each of the mineral names are at the end of their path. So for example, if you look at muscovite here with this blue path, the title is at the end of that path. So let's start with tholeiitic basalt. When I look at these graphs, when I look at these minerals, I looked for markers of specific conditions. So for example, when I see the nesosilicates and inosilicates in red hues, I notice that they start around 250 degrees Celsius and they remain until the end. We don't see them in higher pressures or lower temperatures, so they are a marker of high temperature and low pressure. If we were to find them on Venus, we could assume that Venus once had lower pressures. Mesolite in orange shows at medium temperatures and low pressures. Carbonates in the yellow, they stop around 250 degrees Celsius and lower pressures. You'll see the difference. I'll show the higher pressures soon. And feldspars appear at every pressures at higher temperatures. Phyllosilicates in darker blues, muscovite and phalagopite, for example, they don't really reach past 200 degrees Celsius unless it's annite, which appears at every pressure at high temperatures. And tremolite and amphibole is a marker of high temperature and low pressure right here. So some differences between the different pressures are there's no tephroite, andradite, diopside, those are nesosilicates, inosilicates. There's no mesolite, no graphite. There's some smectites that survive, but a lot of them didn't. There's no tremolite or phalagopite. in these 50 bar models and above. Quartz is consistent and unbroken at these higher pressures. So previously, quartz kind of gets broken up here. It gets stopped. But up in the higher pressures, it remains consistent and undisrupted. Another observation is hematite is more prevalent in higher pressures, and it goes to magnetite. And carbonates appear throughout. So they used to have a kind of a stopping point in temperature, but now we kind of see them at every temperature for the higher pressures. And feldspars, they have greater temperature ranges as well. Next up, we got our first tessera model. So at 1 bar, carbonates tend to be below 150 degrees Celsius, but at higher pressures, they stay throughout. And once again, we see tremolite at higher temperatures, low pressure. And unlike the 1 bar previously with the basalt, quartz is continuously abundant and undisrupted by mesolite. So mesolite is still at the medium temperatures, and you will see absent in higher pressures. Something new is that the phosphates and sulfates appear. These are in lavender colors. At each pressure, they begin around 100 degrees Celsius. We also have some manganese oxides in gray and black here at higher temperatures. And then we have muscovite, which is a marker of lower temperature, as well as nontronite in green. Moving up in pressure, we lose mesolite, tremolite, bixbyite, andradite, a magnesium smectite. Carbonates can survive at higher pressures, can survive at higher temperatures, and sodium saponite is a marker of low and medium pressures, and it goes away once it reaches 100 bar, but it survives up to 50. Another interesting difference is that alunite is only present in 50 bar and above, making it a marker of low temperature, high pressure. Once again, you can see quartz is undisrupted at all temperatures and pressures for this crust. The anorthosite tessera was actually a little more similar to basalt than granodiorite in its results. Tremolite and mesolite behave similarly to the models before. Smectites stop at around 250 degrees Celsius. Albite starts at about 200 degrees Celsius. Around the same time, quartz makes a comeback. And at 1 bar, the phyllosilicates stop at around 250 degrees Celsius. And we see in red, nesosilicates and illosilicates at high temperatures and low pressures. For phyllosilicates, we tend to see muscovite at lower temperatures and anite at higher. And once again, you can see that quartz is disrupted by mesolite. At higher pressures, there is no tremolite, garnets, inosilicates, nesosilicates, mesolite, minnesotite, magnesium smectites, they're not present. Quartz becomes more abundant, and alunite is only in 50 bars and above once again. So usually smectites had a temperature limit, except for saponite at 50 bar. It's present at about 300 degrees Celsius, so that's an interesting observation. Phyllosilicates in the darker blues also extend their ranges once you're above 50 bar to greater temperatures. We can see albite present at lower temperatures, which is about 125 degrees Celsius now instead of 200 degrees Celsius from before. And at all 3 pressures, we have a hydroxyl apatite, a phosphate, and it behaves pretty similarly. So it is in lavender, and it behaves pretty similarly through all the pressures. We are going to compare the 1 bar models between all 3 crusts. So we've got the basalt, the granodiorite, and the gabbroic anorthosite, and we're going to compare all their 1 bar models for the discussion. In comparing these 3 crusts, I'd like to point out our most significant and interesting findings for a primitive Venus. That's why we selected the 1 bar, because it represents a past Venus. So first, we have inosilicates and nesosilicates. They were always markers of high temperature, low pressure at every crust. The difference between them is granodiorite only presented andradite, while the other 2 had all 3 of diopside, andradite, tephroite, and it really was consistent throughout these models that they stayed at these high temperatures. Mesolite is constantly at medium temperatures and low pressures. In the basalt and anorthosite, however, they disrupt the quartz pathway. The high aluminum oxide content in these crusts forces silica from quartz into the mesolite, and this never happens at high pressures, and it doesn't happen in the granodiorite. The lack of nesosilicates and inosilicates may be related to this, as granodiorite has significantly less of these minerals. Tephroite, andradite, and diopside only showed when quartz was broken up like this. When it came to carbonates, Dolomite, siderite, magnesite, rhodochrosite, and calcite were present in every crust except granodiorite did not show siderite. That was most likely due to less mafic content. And in every crust, calcite was at high temperature, and dolomite and magnesite were at lower temperatures. For phosphates and sulfates, the tessera crust had anhydrite and hydroxylapatite at high temperatures. And northwestite had hydroxylapatite throughout at every pressure. And what's interesting is the basalt had none of these minerals, so therefore, if we do find them, it may show evidence of non-basaltic crust from before the transition. Phyllosilicates mark temperature very well, and each crust, muscovite, is low temperature. Mid-temperature is minnesotite or phlogopite, and annite tends to be at higher temperatures. Finally, I wanted to highlight tremolite once more. It's what I'm most excited about from these models, because in every crust, this amphibole is a marker of high temperature and low pressure. Tremolite has been suggested as a possible water carrier remnant on the surface of Venus, and experimental studies that examined the decomposition rate of tremolite predicted that this hydrous mineral could survive decompositions on Venus over geologic timescales. So, if a spacecraft can detect it, we will know that Venus once had water that participated in geologic and atmospheric processes. It would demonstrate that Venus lost its water over time, rather than having no water ever. In conclusion, the results of this model show mineral and gas phases that were markers of specific conditions during Venus's possible transition from habitable to inhabitable. The presence of tremolite, mesolite, andradite, and muscovite are notable signs of a past climate with lower pressures. This model does not reach current Venus temperatures. It reaches 300 degrees Celsius, not 470, and that is something the program does not allow you to go past 300 degrees Celsius, unfortunately. So consequently, some minerals, especially the hydroxides, may destabilize in modern Venus conditions. However, the existence of many of these phases today could indicate a past temperate environment with stable liquid water. To close out here, I want to say that I finished my NASA internship last summer, and I am currently in my third year at OSU, senior by credits. Since then, I have continued working on my research projects, studying weathering patterns at HCA while I take my courses here at OSU. All my research experiences reinforced my desire to pursue planetary geology. They laid the foundation for a career in research and fostered an interest in studying terrestrial planets and exoplanets. Being an undergrad in geology and doing research gave me the knowledge and confidence to plan out a career I would thrive in. I gained a strong work ethic and the independence to forge my own path and plan projects that were enjoyable, intriguing, and applicable to real-world processes and questions. Over winter break, I applied to planetary science PhD programs, and yesterday I received a formal offer of admission from the University of Washington. I am really looking forward to whatever comes next in my journey. In all my endeavors, I realize the importance of mentorship and collaboration, and I'm very lucky to be presenting at an organization that recognizes these strengths. I hope this talk has given you a useful perspective on undergraduate research and perhaps ideas on how to best support the next generation of scientists. I could not have done all this without a lot of people, so first I would like to thank the AWG Foundation and the Pacific Northwest Chapter for awarding me your scholarship and inviting me to present today. You have provided me with both the confidence and stability to achieve my goals. A special thank you to Marcia, Melanie, and Emily for your help in preparing this presentation. I also want to thank all my mentors who have supported me so much, and I want to highlight these 5 here who wrote me letters of recommendation for the scholarship because they are a huge reason I'm here today. So thank you to Andrew, JC, Kaplan, Ben, and Pam. And a very special thank you to Pam and her hydrogeology lab, past and present members, for being a source of wisdom and inspiration for me. I've learned so much from you all. And thank you to Vincent and his students for my time at NASA Supper for helping me to find my next passion in research. Thank you all for listening to my talk. I will take questions now.
Yeah, thank you, Haskelle. That was an amazing presentation, and I am very impressed and kind of intimidated, honestly. It's been a while since I looked at geochemistry. So yeah, I vote folks to please turn on your cameras and let's ask some good questions. And congratulations on the University of Washington. Just hooray for that.
I'm very excited. I'll be visiting their campus in March, I think.
Hi, Haskelle. I had a question about the microwave digester that you talked about. What exactly is a microwave digester, and how did you use it in your research?
Thank you. Thank you for asking. Yeah, I didn't go into too much depth about microwave digestions, but in OSU's Keck Lab, we have it is a microwave. It's a gigantic microwave, nothing you would want to put food in. But I take soil samples and I combine it with various acids, the most prominent being HF acid. So that required me to get training in HF acid. Quite a scary acid. You have to wear like 2 layers of goggles and 2 pairs of gloves. A lot goes into it. But you throw it in the microwave, it really heats it up, high pressures, and it turns the soils into a solution that you can work with, a liquid. So then I can take that liquid and analyze it using spectroscopy using the ICP-OAS. So it's definitely the most time consuming part of my research. It's just a very slow process. I think to do 12 samples, it takes about 6 to 8 hours out of your day. So, but I am very glad to know it. It's a very useful skill, very powerful.
Thank you very much.
I'm curious to hear more about your research on hydrogeology. So I work on river restoration and streams and a lot of fish passage projects. And I kind of joke to people that like step zero fish need water in the channel on the surface. And so I'm curious kind of like what sort of pathways and timescales you're looking at.
Yeah.
Or maybe I'm just going too nerdy. Who knows?
No. I'll talk specifically about my independent one. I started that during my second year of college, so I'm a third year now, and it started off with helping people do H.J. Andrews field work, which I've dug some soil pits. I've not done overnight stays yet, but I've done plenty of one-day trips, and so that's where I initially got my samples. And when I designed this with Pam, we really wanted to look at weathering because that's definitely more on the geology side, which is what I really want to go into. So to do that, we decided to make tau plots. And tau plots, they show the addition and depletion of elements over a depth. So I wish I could show you some, but for those who are unfamiliar, it's like a bar chart, and this is 0, and if elements are being added with depth, it will go one direction, and if it's being depleted, it will go another. And so using that, we can make a lot of inferences about the weathering of elements from that nearby volcanic arc. And so I'm currently pretty much done with sample collection. Pretty much done with sample analysis, actually. There is one more thing I need to analyze. I've analyzed all the different soils at different depths, but I'm working out how to analyze this bedrock core because it's a core of rock rather than a soil. So once I do that, and the tau plots are actually already coded in R, so once I figure that out, we're going to put it in the tau plot. I'll have my plots, and then what's left is essentially interpretation, and then hopefully I get to present on that pretty soon.
Very cool. Thank you.
Thank you.
Stubborn Goat has a question in the chat. Side note, and not totally directly about your specific presentation, but have you heard about Wolf 1069b, possible new habitable planet?
I have heard about it, not dug too deep into it. I will say that hopefully in my own research at the University of Washington, when it comes to exoplanet studies, which I am very interested in, and I will look into that a little more, there's just so many to keep up with, I think specifically I'm looking into doing biosignature research, so trying to find signs of life on exoplanets. So, maybe that one will have some, and I'll keep that in mind for what I do. But no, I'm not totally familiar with that exoplanet.
Does anyone else in the audience have more? It's the first I've heard of it. Nope.
Take any questions. Anything.
How would you determine exactly how to find life on those planets that you're looking for? You mentioned finding different types of rocks and minerals and the composition of oceans from afar, but without actually visiting those planets, how would you determine if there are signs of life?
Yeah, so I definitely haven't ventured into that just yet, but I can tell you we currently do that with lots of spectrometry spacecraft, so you can definitely look into the James Webb Telescope and what they do there. I think they recently just found evidence of carbon dioxide using the instruments they have on board, and during the first images they released, I believe one of them showed the composition of an exoplanet, not Wolf 1069b, unfortunately, but that's pretty much how I'm aware you do. I'm sure there's way more in depth into that topic, but when it comes to habitability, what I've been doing in this research is finding minerals and gases that indicate at some point stable liquid water. So that's how I've been doing it thus far.
Very cool.
Yeah, Rob, go.
As a woman in science, how have you found support among some of your other colleagues and kind of venturing through some of that? And then looking forward as you go to UW now, thoughts about how you might wrap yourself with support or be supportive of others as you move on along in your field?
Okay. I was very fortunate to be in a lab that has lots of women. Dr. Pamela Sullivan's lab has lots of women who I look up to, and I ask them a lot of questions. So that's how I felt really supported, is I've been able to talk to a lot of people who are like me. And I'm very fortunate to be at a university that I believe, that takes diversity very seriously. So even though, a lot of my professors are not people with my identity and background, they take a lot of time to understand where I come from, and they try to appreciate parts of my identity when they're offering opportunities. And for example, when I go to conferences, they give me a lot of support. For example, there's this saying that you should never eat lunch alone, but it can be hard as a woman to want to go into a table filled with all of men and try to introduce myself. And so learning those techniques and from people who feel way more comfortable doing that, for example, professors, has definitely, all those resources have made me feel a lot more supported. Going into the University of Washington, yeah, that's a great question. I think I'm definitely transitioning out of a comfort zone here. I'm transitioning out of a place I feel very at home. I'm from Oregon, and to find support there, I'm gonna lean on my advisor quite a bit, because that relationship is very integral to a PhD program. So leaning on my advisor for help, and leaning on trusted people, whether that be my own people I can call friends, through people who are also PhD students, or maybe other professors who are like me, fellow women professors, or just professors who appreciate the differences that may occur. I think that's where I definitely will draw a lot of support. I am definitely a people person when it comes to support, and I love talking to people, getting different perspectives, and so that's what I'll probably continue doing. Thanks, Rob.